Alright, so the next problem is problem number 2322, which is marked as a hard level problem, and the title is minimum score after removals on a tree. So there's an undirected connected tree with n nodes labeled from 0 to n-1 and n-1 edges. You're given a 0 indexed integer array, nums of length n, where nums of I represents the value of the ith node. You're also given a 2D integer array, edges of length n-1, where edges of I is equal to ai, bi, indicates that there's an edge between nodes ai and bi in the tree. Now we need to remove two distinct edges of the tree to form three connected components. For a pair of removed edges, the following steps are defined. Right, so get the XOR of all the values and the nodes for each of the three components respectively. So basically we remove two distinct edges from the tree to form three connected components. For a pair of removed edges, we need to get the XOR of all the values of the nodes for each of the three components respectively. And the difference between the largest XOR value and the smallest XOR value is our score of that pair. And we need to return the minimum score of any possible pair of edge removals on the given tree. So for example, say the three components have the node values 4, 5, 7, 1, 9 and 3, 3, 3. So basically, let us say the components are formed in such a way: 4, 5 and 7, right? 4, 5, 7, 3, 3, 3. Let us say this is the next component, and then we have 1 and 9, right? So these are the three components of the graph, and initially they might have been connected. So we removed any two edges. Let us say these were the edges. So we removed these edges. Two edges were removed, distinct edges, to form these three connected components. So one component, second component, and the third component. And then we need to get the three XOR values. So 4, 5, and 7 we get the XOR as 6. Then 1 and 9's XOR is 8, and 3 XOR with 3 XOR 3 XOR 3 is equal to 3. So the largest XOR value is 8, and the smallest one is 3. So the score is difference between the maximum XOR value and the minimum XOR value, that is 8 minus 3 is equal to 5. Right, so that is the problem, and now let us get to the example 1. So basically, this is the nums given to us, that is the values of each of the cell or the node. So 0, 1, 2, 3, 4. So these are the nodes, and the values respectively assigned to them have been marked with blue on either top of them or on the side. So we have 1, 5 for this as well, and then we have 4 for the node 3, and for node 4 we have 11. So basically nums we have done, and then edges basically is denoting the adjacency list that will be formed. This is not the adjacency list, we'll form the adjacency list on our own. This just denotes the edges that we have between the nodes. Now we see that we remove these two edges. Let us say we remove these two edges, and then we have the connected components as this one component, then we have this component, and then we have the third component. So the first component has nodes 1, 3, 4 with values 5, 4, 11. Its XOR value we get as 10. Then this has an XOR value of 1, and this one has an XOR value of 5. The score is the difference between largest and smallest XOR value, so we take 10 minus 1 is equal to 9. And it can be shown that no other pair of removals will obtain a smaller score than 9. Okay, so that's our first example. Then we have the next example as this, right? So the values marked with blue are the nodes value that we have to take into account, and the ones that have been marked are basically the indices or the node index, right? So yeah, and the edges, we form the edges. So then basically we see that we are removing edges pairwise. So a way to make a pair of removals, so let us say we remove these two edges. The first component has nodes 3, 4, then next component is 1, 0, and third component is 2, 5. So we get the XOR values 0, 0, 0, and the maximum difference is actually, sorry, the minimum difference, the score is the difference between largest and smallest XOR value, which comes out to be 0. And we cannot obtain a smaller score, so that is the minimum score or the minimum difference we needed, right? So that's it about this examples part. Now let us get to the solution part. So basically in this problem, let us start with our intuition. So a tree with n nodes has exactly n minus 1 edges. Removing two edges splits the tree into 3 subtrees. So let us say we have this graph as I just showed you, right? So removing two edges would actually split the tree into 3 subtrees. So let us say we remove, let us say we have another edge here and another node here. Let us say we remove this one and this one. So you see one connected component, another connected component, and the third connected component. So when we remove two edges, we get 3 subtrees. And XOR is associative and reversible. So A XOR A would be 0. So the XOR with the same value would be returning 0. Then A XOR 0 returns the value itself, A, and A XOR B XOR C is the total XOR. So these are some properties of XOR that we'll be using in the problem. And the problem is exploring all unordered pairs of edges and computing the component XORs. So this is the most important part, that every tree has n minus 1 edges. We need to remove two edges, which divides the tree into 3 subtrees. So XOR is also associative and commutative. Using the Euler tool technique, we need to track our ancestor relationships and use DFS to compute subtree XOR of I, which is XOR of values in the subtree rooted at I, and in time of I and out time of I for Euler tool to detect the ancestor descendant relationship between any two nodes U and B. So our approach is simple. We build the tree, use the adjacency list from edges, right? So we build the tree first, then preprocess with DFS. That is the Euler tool. So let me show you side by side what I'm going to do in our problem. So firstly, this is our main function, minimum score. So what I've done here is, firstly, I've just simply created the adjacency list in this format, unordered map of int, vector of int, and I populated this adjacency list. So this is undirected graph. So u to v and v to u, we have edge, right? So I first created the adjacency list from our edges, right? And now we pre-process with DFS, that is, we call the Euler 2. So firstly, we compute the subtree of XOR of I, which means the XOR of all values in the subtree rooted at node I. So vector of int type subtree XOR of subtree XOR would basically be storing XOR of values in the subtree rooted at node I. And then we define in time of I and out time of I. So basically, these are two vectors, in time and out time, which would be storing the time. In time would store the time that we reach the node in a DFS call, and when we reach it, basically when we are entering the node, and out time would be storing the time we are exiting that node from DFS. So in time of I is the time when DFS enters node I, and out time of I is time when DFS exits the node I. Now, this would help us determine if a node is an ancestor of another using the formula this one, right? So I'll get there in a few seconds, in a few minutes. First, let me just take you through this, what we are doing. So we declare time is equal to 0, okay? Then we start a DFS from root 0 to fill in the subtree exhaust, these values, and the Euler 2 timings. These are the Euler 2 timings in time and out time vectors. And in result, in that we store our int max initially. So now we are going for all possible pair of nodes n and explore them. So we try all pairs of u, comma v, where u and v are not are nodes and are not equal to root, that is 0, since we are starting from 0. Okay, then we try all unordered pairs of non-root nodes u to v. Three possible cases can be existing. So basically, if u is an ancestor of v, let us say u is this node and v is the child of it. So it could also be something like this. There may be other nodes, right? And it's not necessary we have this in the same, like, it should not be, it's not necessary it is u is necessarily a parent. It could be a v could be a grandchild of u, or it's a great grandchild of u, right? So this means that u is an ancestor of v. Okay, so in that case, we basically first declare XOR1, XOR2, and XOR3 for storing the values, and we're going over all the pairs when nodes are not equal to root. So if u is an ancestor of v, so we call this function. So we get the XOR of v first, then use XOR we'll get from XOR of v with itself. So we compute the three values, XOR1, XOR2, and XOR3. XOR of basically what we are doing is that we have the root. Okay, this is root 0, and let us say we have node u here, and we have v, let us say, somewhere here. So u is an ancestor of v here. Oh, sorry, v, yeah, and v is basically the it could be the, it is a, basically it is coming in the subtree of u, right? So basically what we are trying to do is we first get XOR1, that is the value at node, the value of the XORs of value of XOR of the nodes rooted at v, right? So we get the XOR value here from that. Then XOR2 would be basically storing, XOR2 is basically storing our value of u and the XOR that we received from v. So basically it computes XOR of u, the whole under this subtree of u, we get the value in XOR2, and finally for XOR3 we calculate the subtree XOR of 0. So basically the whole tree's XOR value is stored here, and we XOR it with the u and v XORs. Third component, root XOR, that is from the ones the left subtree and the right subtree from the v. Else if v is the ancestor, then we basically just replace it. So XOR1 is subtree XOR of u, XOR2 would be subtree XOR of v and XOR with XOR1 value, and finally same for this XOR3 from the root and XOR1 and XOR2. And in case u and v are not ancestors, so they are in a different, basically they are different siblings. They could be siblings, or they could be away, not in the same pool, right? So in that we just calculate subtree XOR from this side u and from this side v and the root 1, and we get the minimum of the get score of XOR1, XOR2, x3, and min score function is basically this function, which would basically giving us the score function, which is max minus min of the three XORs. It takes three values ABC. We get the max XOR and the min XOR, and we subtract it. That is our final answer, right? So for each XOR we calculate the XOR total XOR, XOR1 and XOR2, update the minimum score, and this is the same function, that is max of XOR1, XOR2, XOR3 minus min of XOR1, XOR2, XOR3. And the complexity is O of n square for trying all node pairs u, v, O of n for DFS traversal. Overall, we are getting O of n square, and space complexity is we're using adjacency list and three vectors, subtree XOR in time, out time. So all are all take O of n space. And now let us go. Is ancestor function is basically going to take, using the Euler 2 technique. We check for u and v. So let us say we have this node u and we have the node v, and basically we're basically performing DFS, right? So Euler 2 uses the DFS function, and in time we will be populating it. So firstly, let us say at time t is equal to 1, we get at node u from basically any other node. So u is the node that we get to from the DFS function. So in time of u is basically stored as 1. Then we go to v. So we increment the time. Obviously, in time of v becomes equal to 2, right? So we are going here at the next step. Now we exit it because we have let's say it has no other children. So DFS call returns false, and we basically get out. Okay. So basically its exit time would be 3. So out time of v would be 3, and then finally we are also coming out of u. So out time of this would be 4. Out time of u is 4. Out of time of u is 4. So this is the same condition that we return in time of v greater than equal to in time of u. That is, this value 2 is greater than 1. Yes, it meets the condition. And out time of v is less than equal to out time of u. So out time of v is less than equal to out time of u. 3 is less than equal to 4. So this is actually the condition, which means that u is visited first, and then we find in the subtree that we are visiting, we will find v at a later stage. So that means that u is visited first. So u would definitely be at an ancestral level of v. So it would be somewhere above in the tree, above in the hierarchy. So this is the condition for that. So this is called the Euler-Tour technique. So we use that, and basically DFS to compute in out time and the subtree XOR. So we're taking node, the parent of that particular node, subtree XOR, in time, out time, all passed by reference. So because we need to update this, and time also we pass as reference because that would also be updated, and nums as well, and another map, basically the adjacency list that we're storing. So first, for the subtree XOR node, we assign nums of nodes. So initially XOR is the node's own value, right? Since we are taking the node's value, and XOR of itself would be the node's value. Okay. Then in time of node we set as time. So this time we're starting. So store the time when we are entering this node. Then time plus plus. Now we perform the DFS. That is, we are traversing for each neighbor. So we go over all the neighbors of this particular node. We go over all the neighbors. That is the children, right? This is not a directed graph, but this is going to the children. So if neighbor is not parent, that is, if the neighbor is not the parent of this particular node, then we actually call the DFS again, and now the node becomes the neighbor and the parent becomes the node, because we are starting from node, and neighbor's parent would actually be node itself. So that is why we are passing this. And now subtree XOR of node is equal to subtree XOR of that node and the neighbor's node. So we get the XOR of this particular node by going to all its neighbors that are present within this tree. So from all the child subtrees, we get the XOR value, and then this is the XOR value. We XOR it with the node's value. After DFS, this would give us the subtree XOR, and then we XOR it with the node. So this is the same thing that is done, subtree XOR of node and the neighbor. So that would be done from the DFS call, and we store it in subtree XOR of node. And finally, once we have completed our DFS, we have to also store the out time. So store the time when we are exiting that particular node, and increase the time also, that you need to remember. So this is our whole function and whole solution to this problem.